Okay, perfect. So we start with some introduction about the past fire accident around the world. You will see some example, specific example happened in 2007. And you will see also some the introduction of the case study, talk also about the fluidodynamic computational, but also how we implemented in SAFIR for the thermomechanical analysis. And then we will see the results of both of them and also how we managed to couple this data. And we will see also some conclusion and some things that we are currently working on. This is like an overview, and this presentation provides an overview of how we couple the data coming from the computational fluid dynamics analysis to perform also thermomechanical simulation using the SAFIR software. And the outcomes of the thermomechanical analysis and the methodology we use will be illustrated in this presentation. But first, I want to move on to the motivation background of this research project that we are currently investigating. And pipe racks are essentially structured in many industrial and petrochemical plants and are providing the necessary support for pipelines transporting various material across facilities and also tanks. The industrial environment increases also the risk of emission from released flame materials, and despite their low probability, they pose a catastrophic risk. Major fire accidents involving the pipe racks occurring around the world. Here you can see 6 examples that happened in the past from, for example, the accident happened in February 16, 2007, that I will explain better in the next slide, but also happened in China in a biofuel plant. It happened also in Russia. It happened also in Iran in 2023. Again, it happened another one in Texas in 2023, but also happened in Italy at the end of the last year in a facility near Florence. Okay, so here you can see what happened during the McKee refinery fire accident happened on February 16, 2007. The fire occurred in a unit that used large amounts of high-pressure liquid propane. Years early, the unit had been reconfigured and creating a dead legor, that is a section of piping without any flow of liquid. Over time, small amounts of water, which were contained to the liquid propane, sank past the leaking valve and accumulated in the piping below. On February 15, the temperature fell to -14 degrees Celsius and the water froze, expanded and cracked the pipe. The following days, as the weather warmed, the ice melted and the propane began exit from a broken pipe, and the wind carried the propane cloud toward to a boiler house where it likely found a spark to ignite the entire cloud. Immediately, flames shot back to the source of the propane leak. Flames attacked the nearby piping, and as the pipes carrying liquid propane failed, a high-pressure jet of flaming propane launched itself at a steel column around a pipe rack filled with petroleum products. This steel column did not have fireproofing, and it collapsed under the flames within minutes. The pipes broke and the fire intensified as it filled on more propane, and the fire seriously burned 3 people and shut down the facility for 2 months. Okay, so here you can see the case study under consideration, and is a typical unprotected portion of a pipe rack structure, a structural steel element typically used inside the industrial plants. This structure primarily developed in length with support of platform for pipes and cables and with ground clearance at least of 5 meters so as not obstruct the traffic. Here you can see the portion that we are currently studying, and you can see that is connected to a tank capacity of ethylene gas. The total length of the select portion of the pipe rack is 77.8 meters and is subdivided into 2 spans, 47.3 meters and 30.5 meters. The height is 11.7 meters and the width is 4 meters, as shown in this slide. The brace frames are fixed at the ground, brace and transversal beam are hinged at the ends, and also the other elements are hinged in plane. The truss bridges are considered simply supported on the support brace frames, and an S235 steel grade was used for all the steel elements that you can see in this slide. First, a validation of the Jetfire model methodology based on the literature review and the comparison against experimental data was performed. I will start with some consideration and validation about the fire dynamics simulation software before moving to the SAFIR part, and that is possible also to find in these two documents that is below on the bottom right part of the slide. In particular, I will take the validation of one of the Jetfire experimental performance in UK in the past as an example for the model of the Jetfire inside the FDS software. In fact, fire dynamic simulator is not able to direct model the flow at the pipe gas leak. However, it is possible to model some jet fires using specific methodologies and parameters without exceeding the software limitation. For example, cold gas droplets are injected in the domain with a high initial velocity and a relatively narrow spray angle. These droplets evaporate very quickly to form the proper gas and to create the jet fire. In fact, you can see here that the fire dynamic simulator is developed for low Mach number and is below 0.3 or about 100 meters per second if we consider standard airflow. There is some trial and error involved in the prescribing and simulating a jet fire. But the most important consideration is to match the mass flux and the to qualitatively capture also the spray angle. The jet fire formulation is described in several books and papers. This slide summarizes the main equation and that describe the basic concept and how the FDS parameters were calculated. But for a comprehensive and in-depth jet fire formulation, you may refer to specific literature, for example, the one that I put at the bottom of this slide here. In summary, the characteristic of the gas flow depend on factors such as the gas type, the temperature, and the pressure. The flow can be either shocked, meaning the gas exits at sonic speed, so Mach number equal to 1, or subsonic, where the exit velocity is below the speed of sound, so the Mach number is below 1. There is also another possible condition that I didn't include in this slide, that is the supersonic condition, where the Mach number is higher than 1. For brevity, I don't have time to explain every single analysis that we perform. So one simulation, I selected one simulation as an example of the scenario model in FDS that involved a methane leakage from a pipeline located on a parallel pipe rack or nearby tank. This table reports the parameter that we use in the previous equations. In detail, the methane droplets were ejected from the nozzle at an initial high speed of 400 meters per second with a median diameter of 1,000 micrometers. The spray was directly within a narrow cone forming a 5 degrees angle, and each second a maximum of 1 million droplets were introduced into the simulation between the nozzle. At the nozzle, the mass flow rate was 1.9 kilogram per second, corresponding to a volume of 2.9 meter cube square per second. To account the flow losses caused by the friction as the gas passed through the crack, a discharge coefficient was also considered equal to 0.8. And for the computational fluid dynamic analysis, the first step is to create a 3D model of the pipe rack in order to have the obstruction surface for the flames and the smoke. It is also important to select and describe the fire scenario. For example, here, a jet fire that impacts the middle part of the left span. But another scenario could be, for example, the jet fire that impacted the central columns of the pipe rack. Then it is possible to run the computational fluid dynamic analysis using FDS software and obtain the surface temperature of the pipe rack elements and use this temperature data to perform the thermal section and the thermomechanical analysis using SAFIR software. A 3D model of the portion of the first span of the pipe rack was created in FDS. The model domain is 36 meter wide, 15 meter deep, and 10.4 meter height to allow for sufficient volume for air to circulate and the extension of the flames. All boundaries were left open to the ambient and the initial temperature was set equal to 20 degrees. The absence of the wind was set during all the simulation, and a good balance between accuracy and the computational cost was chosen to run the FDS simulation in a reasonable time. A more refined mesh was used in the area near the nozzle, and the domain was subdivided into 16 subdomains in order to optimize the computational time by running in parallel using 32 CPU threads. The jet nozzle was located 8 meters in front of the pipe rack and 7.4 meters above the ground, corresponding to the height of the lower longitudinal beam of the pipe rack. In order to measure the gas temperature evolution of the pipe rack components, a total of 9,687 adiabatic surface temperature devices or adiabatic surface temperature gas devices were placed on the pipe rack. The output values of these devices were used to perform thermal structure analysis of the section in SAFIR. This slide illustrates the development of the fire and smoke after 40 seconds from the beginning of the jet fire scenario as an example of the fire development stage. On the right, you can see also the adiabatic surface temperature as a result of the jet fire. And despite the cold methane droplets were inserted in a high velocity 400 meters per second, you can see that the bottom plot demonstrates a high velocity flow remains within the acceptable low Mach limit of the FDS software. A 3D thermomechanical model of the portion of the pipe rack was created in the thermomechanical finite element software SAFIR using nonlinear beam elements based on the rotational formulation. Usually for pipe racks with large spans where exceeding, for example, 40 meters, bracing towers are introduced to absorb horizontal forces. In this case, the tower was not directly modeled in the thermomechanical analysis. However, an accurate modeling of the actual boundary condition represented by the other portion of the pipe rack with the bracing towers also included were considered using some spring elements that you can see on the left part of the model. In detail, a pushover analysis was performed to determine the equivalent stiffness to assign the spring element, and geometrical imperfections were also included to allow the flexural buckling of the compression members. In this slide, you can see the gravity loads applied to the pipe rack and the axial force of the gravity analysis results. For the first analysis, we didn't model directly the pipes, but we considered the load applied them. And this other slide, you can see some deformation of the pipe rack that is enlarged by 10 times for only the gravity loads. In order to use the data of the 9,687 adiabatic surface temperature devices, a specific software developed was used for the automatic creation of the running of each heat transfer section analysis. In this slide, you can see the measure steps. First, the framework loads the inputs of the data from the adiabatic surface temperature devices and also the data of the SAFIR model to automatically post-process the data of these devices. Then the framework identifies the section of each SAFIR elements and create an input thermal file with the actual frontiers based on the data of the sensors. In this case, a total of 605 different thermal sections were automatically created for the hot part of the pipe rack. The thermal section were employed for the thermomechanical analysis of the pipe rack, which was performing using the SAFIR software. Here, as an example, the slide shows some thermal section of the upper front longitudinal beam and one front stanchion and also one horizontal brace. It is also possible to notice that the difference above 100 degrees between some section points and the temperature in the cross-section that exceed 750 degrees. In this animation, you can see on the top left the FDS analysis. On the right, you can see the deflection of the beams, in particular at some point of the middle point that you can see in the right part. The horizontal displacement of the pipe rack. On the bottom left, you can see also the deformation and the temperature of the section. On the right part, bottom part, you can see the deformation. And the structural collapse happened after 90 minutes due to the failure at the mid-span of the truss bridge in the pipe rack. Failure was caused by the loss of strength and material fracture in elements exposed to direct flame impact. In this slide, you can see better the failure that occurred there. And in particular, you can see better in the last step of the deformation of the SAFIR model. You can see on the left the deformation shape along and also out of the plane. And you can see the vertical displacement of the two nodes and the out of plane displacement of these two nodes. On one model that we are currently working is to include the direct model of both the pipeline and also the pipeline pipe rack joint. In this slide, you can see some picture of one possible joint type that are commonly used in this type of structures. And another task that we are working using SAFIR thermomechanical model is the problem associated with the wildfire industrial interface, and will be also analyzed in this kind of research as a possible hazard scenario for industrial plants that are located at the vegetation boundary. On the left, you can see a picture of a wildfire happened in Los Angeles at the beginning of this year. And from January 7th of the beginning of the year, a series of 14 destructive wildfires affected the Los Angeles metropolitan area and also the San Diego County in California. On the right, you can see that the wildfire hazard map of Europe, and you can see that there are a lot of areas with a high or intermediate risk of wildfire. For that reason, in collaboration with also the University of Bologna, we are also studying this topic. In detail, we are taking into account three types of vegetation: the grass fire, the shrub fire, and the forest fire, with different vegetation height between 1 and 10 meters. And also with a different flame length between 7.5 to 35 meters, with different also tilt angle of the front of the fire between 70 degrees and 90 degrees. That change also the maximum irradiation will be between 10 and 70 kilowatt over meter square. And the different fire front spread between 2 and 28 meter over minutes. We also take into consideration different height, different point of the pipe rack in order to have different thermal section. We also create another framework in order to automate create this thermal section. We also include the part of the exposition direction to include exactly where is the fire to expose of the maximum irradiation and to take into account where is hiding or shading between other elements will be 0. On the right, you can see some preliminary example of one of these forest fires. You can see the deformation scale, the shape of failure of the pipe rack, and also the vertical displacement in 2 points. Of course, this is an ongoing project that is found inside the ReLuis project, and it is also in collaboration with the Italian Civil Protection, and aims to study the structural vulnerability model for natural hazard and industrial cascade effects. And for future perspective, we are planning more other jet fire analysis and also wildfire analysis in order to develop some fragility function based on the thermomechanical results. So jet fires are rare, but can cause a lot of damage, especially to unprotected structure, and especially when we are near other pipelines that can be broken. In the example that I showed you before, structural collapse occurred after 9 minutes due to the failure at mid-span of truss bridge in the pipe rack. And non-uniform heating lead to significant temperature difference, especially in the flame where is affected by the jet fire. And understanding the impact of the jet fire on structural integrity is crucial in developing effective safety protocols and engineering design to mitigate the risk in industrial environmentals. So thank you very much. And if you have some question, I will be happy to answer it.